So if you feed a standard vision model, like a million images of a golden retriever, it processes the features
Oh,
flawlessly.
yeah, absolutely
Right.
flawless.
I
Yeah.
mean, it maps the geometry, the textures, and it outputs this really highly confident classification.
Hmm.
But then if you show that exact same model, like three images of a rare terrestrial snail, it effectively goes blind.
Yeah, it completely
Right.
flips
It's
out.
wild. And the classification landscape that we rely on for real-world deployment, well, it isn't balanced at all. It is heavily skewed.
Extremely skewed, yeah.
And dealing with that long-tailed distribution is basically one of the most stubborn bottlenecks in deep learning right now.
It really is.
Mm.
Because the problem scales so poorly, since real-world data just inherently follows that long-tailed distribution.
Right.
Like we always have this massive concentration of data in a few head classes and then this vast, really sparse tail of rare class.
Edge cases.
Exactly.
Yeah.
And when you run an imbalanced data set like that through standard backpropagation, the gradients are just entirely dominated by the head classes.
Because there's just so much more math pushing in that direction, right?
Precisely. The network optimizes for the path of least resistance. So it minimizes overall loss by prioritizing the patterns it sees constantly.
Okay.
And the mathematical signal from the rare classes is simply washed out. It
Yeah.
just gets drowned in the noise.
Well, welcome to the deep dive. Today, we are analyzing a framework that tackles this specific vulnerability.
It's a really exciting one, too.
It is, yeah.
Yeah.
We're looking at a paper from Tianjin University, and it's titled Long-Tailed Classification with Multi-Granularity Semantics.
Right.
And the core mission of this research is basically to move away from just brute forcing the data set.
Which we know doesn't work.
Right, which fails. And instead, they want to teach a vision model to utilize prior semantic knowledge, which is heavily inspired by human cognitive processes.
Mm.
They implement this thing called semantic knowledge-driven contrastive learning, or SKCL.
SKCL,
And they use an LLM as a teacher to guide the representation learning.
which is such a clever approach.
It really is. And for everyone listening, this matters because it outlines this pathway for AI to achieve robust generalization, but with significantly less raw data.
All right, you don't need a billion images of everything anymore.
Exactly. It bypasses those standard zero-sum trade-offs we always see in long-tailed classification.
Yeah, to really appreciate the mechanics of SKCL, I think we first have to look at why the conventional approaches hit a wall.
Okay, yeah, let's get into that, like resampling.
Right, resampling strategies. They're essentially dead ends for generalization.
Why is that?
Well, if you oversample the tail classes, you're forcing the model to repetitively process the exact same pixels over and over.
Oh, so it just memorizes them.
Yes, it leads directly to overfitting. The model memorizes the specific background of those three snail images, rather than learning a generalized representation of the snail itself.
So it thinks a snail is just whatever that specific leaf in the background looks like.
Exactly. And then on the flip side, undersampling the head classes is equally problematic.
Because you're throwing away good data.
Right? You are actively discarding valuable feature variants. And that degrades the overall robustness of the model.
Okay, so resampling is out. And I know the older transfer learning methods didn't fare much better either.
No, they really didn't.
Because they tried to push weights from the head to the tail, but without any real semantic alignment.
Right, they just forced it.
I sort of compare this to like a library where 90% of the books are Stephen King novels.
Okay, I like this analogy.
Right, so that's your head class. And there is like one textbook on quantum physics, which is your tail class.
Right.
If you force the librarian to learn quantum physics using the rules of a Stephen King novel, it's just a disaster.
It would be terrifying, but useless mathematically, yeah.
Right, so if you try to map the robust features of a dog onto a rare airplane class just because one has lots of data and the other doesn't, you trigger negative transfer.
Exactly. The model attempts to find quinine features on an aerodynamic chassis.
Which is ridiculous.
It is. The gradient updates just become contradictory noise. You can't just pass weights around blindly. The transfer has to be conceptually relevant.
Okay, so if brute force fails and blind transfer fails, how do we fix it?
Well, human cognition actually avoids this trap entirely by relying on multi-granularity semantic structures.
Multi-granularity. Okay, break that down for me.
Sure. So when a human encounters a novel or rare object, we don't attempt to process it in a vacuum.
Right, we compare it to things we know.
Exactly. We instinctively map its features against this vast web of prior knowledge at varying levels of detail.
Okay.
So like if you see a highly obscure specialized piece of construction equipment for the very first time, You immediately infer its properties.
Like I know it needs fuel.
Right, it requires fuel, it possesses hydraulics, it probably moves really heavily.
Because I'm mapping it conceptually to standard bulldozers or cranes that I've seen before.
Exactly. We bridge the data deficit by leaning on those shared concepts.
But standard deep models can't do that right, because they are bottlenecked by fast, rigid label hierarchies.
Yes, things like WordNet.
Right, WordNet, it organizes classes strictly by, like, categorical or biological lineage.
Which is very rigid.
Yeah, it is. And the paper has this great example. If we look at how it structures a turtle and a snail, the limitations become incredibly obvious.
Oh yeah, the turtle and snail example is perfect for this.
Right, because WordNet places the snail deep inside the non-insect invertebrates branch, while the turtle is nested way over under the reptiles branch.
So under that rigid topological structure, the distance between a turtle and a snail is just massive.
They're miles apart in the data tree.
Exactly. The network's logic dictates that these two classes are entirely disconnected.
To get from one to the other, it has to go all the way up to the root node of animal and then back down a completely separate lineage.
Right, which means it shares zero visual or functional assumptions between them.
Yet, if you just look at them through a functional or a visual lens,
Yeah.
the turtle and the snail share significant cross-branch similarities.
Oh, absolutely.
I mean, both possess a prominent protective hard shell, right?
Right.
Both are ground-dwelling, they're slow-moving, and they both utilize shell retraction as their primary defense mechanism.
It's a very specific shared survival strategy.
Yeah, so a semantic mapping recognizes that shared strategy and those shared visual features. But the traditional hierarchical subtree is completely blind to it.
Right, it just sees reptile versus invertebrate.
So the researcher's objective here is to build an architecture that's capable of jumping across these static subtrees.
Right, they want to share representations based on conceptual similarity rather than just strict biological classification.
Okay, so we know what we want the model to do. But the fundamental challenge is that a categorical label, like just the string of characters for the word turtle, it contains virtually no semantic density.
None at all. A vision architecture cannot extract the concept of a hard shell from an isolated text label.
It's just a word of the computer.
Exactly. So to operationalize this multi-granularity knowledge transfer, the framework introduces a teacher model.
Okay, the teacher model.
Right, this teacher is capable of injecting rich, prior semantic knowledge into the training pipeline.
And this is where they utilize large language models
Right.
to map these conceptual relationships.
Yes, they bring in LLMs like ChatGPT or DeepSeek.
See, integrating an LLM here is such a fascinating architectural choice to me, but it seems like it immediately introduces a huge data structuring problem.
It does. It can be very messy.
Because if you just prompt an LLM for a description of a specific class without strict parameters, the variance in the output is massive.
Oh, totally. You might receive a dense biological taxonomy for one class and then like a generalized cultural reference for another.
Right, like if you ask about a dog, it gives you a poem, and if you ask about a beetle, it gives you a Wikipedia article.
Exactly, and that variance completely breaks the vector space alignment downstream. The math just won't work.
So how do they fix that?
That is precisely why the prompt engineering in this methodology is strictly constrained. They don't just let the LLM ramble.
Okay, so they force a structure on it.
Right, the researchers standardize the LLM output using a really specific template.
What's the template?
It asks for a description of the class based on its appearance characteristics and behavioral traits or functional features.
Oh, okay. Appearance and behavior. That's very targeted.
Extremely. And furthermore, they instituted a hard cap of 300 words per response.
300 words max.
Yes, enforcing that structure ensures uniformity across the feature space.
So by constraining the LLM to just appearance and behavior, they basically guarantee that the downstream math is comparing equivalent conceptual parameters.
Right, they're making sure the model compares apples to apples. You don't want it comparing a physical description to a historical one.
That makes sense.
Yeah.
But I do have a question regarding the reliability of the LLM as a teacher.
Sure, what's the concern?
Well, LLMs are notoriously prone to hallucination, right? Especially regarding the physical properties of, like, highly obscure edge cases.
Oh, absolutely, they hallucinate all the time.
So if the LLM generates a slightly inaccurate physical description of a rare tail class, doesn't that corrupted prior knowledge sort of poison the subsequent representation learning?
It is a really valid concern. But the framework mitigates that risk by focusing on macro-level semantic alignment.
Okay, macro level.
right? It's not relying on the LLM for pixel-perfect truth.
I see.
The LLM isn't replacing the visual data at all. It is merely guiding the contrastive loss.
So it's just a nudge in the right direction.
Exactly. Even if an LLM slightly mischaracterizes a minor behavioral trait of a rare beetle, the macro-level visual descriptors remain highly correlated.
Like the fact that it has a carapace or possesses 6 legs.
Right, those things are still accurate enough to group it with other similar insect classes.
Okay, so the visual backbone is still anchoring the core feature extraction.
Yes, and the LLM is just providing the gravitational pull toward the relevant semantic neighborhoods.
That completely clarifies the integration for me. So the LLM generates these structured text descriptions for every class in the dataset.
Yep, every single one.
But a vision model can't read paragraphs. It only speaks math. So to make this actionable for the vision architecture, the text is fed through a sentence transformer.
Specifically, the all-middle LM L6v2 model.
Right, and that model maps these descriptions into a 384-dimensional vector space.
Which is where the real magic happens.
So each description becomes a point in this huge 384-dimensional space.
Right. And critically, before they apply any similarity metrics to these vectors, the pipeline executes L2 normalization on the embeddings.
L2 normalization. Okay, pretend I'm terrible at math, which I am. What does that actually do?
Sure. Basically, by projecting all the 384-dimensional vectors onto the surface of a unit sphere, the framework neutralizes magnitude discrepancies.
Magnitude discrepancies, meaning like if one description was 50 words and another was 200 words.
Exactly. It neutralizes any variations caused by residual differences in the LLM's vocabulary choices or length.
Oh, wow. Okay.
So the semantic value is strictly isolated to the directional angle of the vector, not how long the vector is.
I love that. I sort of compare this to like mapping stars in a galaxy.
Okay, let's hear it.
So even if the bird constellation and the airplane constellation are far apart on that old WordNet map in this new 384-dimensional sphere, they are suddenly right next to each other.
Yes, because their semantic vectors point in the exact same direction.
Right. It allows the model to compute a semantic similarity matrix with a really high degree of fidelity.
And that matrix is everything. The model computes the cosine similarity between all the class vectors.
And that dynamically generates what they call a multi-granularity semantic knowledge graph.
Right. It actively identifies the top k most similar classes for any given object.
So returning to our earlier example in this new feature space, the snail and the turtle vectors would exhibit high cosine similarity.
Very high ER. Which establishes a direct semantic bridge that completely bypasses that rigid WordNet topology.
We finally connected the snail and the turtle.
We did. We have the map now. We know who is similar to whom based on actual concepts.
So with that map, with that semantic similarity, Matrix generated the architecture transitions to the two-stage framework to execute the actual learning.
Right. Stage 1 is where we build the centers of gravity.
Prototypes.
Exactly. The first stage focuses on constructing stable multi-granularity prototypes for each class.
And how do they build those?
The model trains linear classifiers across different hierarchical levels, and then the weights from these classifiers are passed through a multi-layer perceptron, or MLP.
Okay, and the paper specifies just a single hidden layer for that MLP, right?
Yes, just one hidden layer.
See, using a deeper MLP might seem intuitive if you wanted to capture more complex nonlinearities.
People often assume deeper is better, yeah.
But in this specific context, I assume a deeper network risks severe overfitting on those relatively constrained semantic embeddings.
That is the exact rationale perfectly stated. The goal of the MLP here isn't to learn entirely new features from scratch.
It's acting more like a translator.
It is acting as a projection head. It maps the raw visual features into a subspace that aligns with the semantic embeddings we got from the LLM.
Oh, okay.
So a single hidden layer provides enough capacity to refine those weights into a stable representative prototype without overfitting on the 384-dimensional vectors.
Got it. And these prototypes serve as the stabilized mathematical anchors.
Right. They are essentially the perfect mathematical ideal of a specific class.
The idealized representations across different granularities.
Exactly.
Which brings us to the core mechanism, stage 2.
Semantic knowledge-driven contrastive learning.
Yes, SKCL.
Yeah.
So as we discussed, the rare tail classes suffer from really weak, highly unstable gradients.
Because they just don't have enough image samples to learn from.
Right. So SKCL addresses this by utilizing the semantic similarity matrix to essentially pull these weak representations toward the robust prototypes of their top case similar classes.
Yes, it borrows gravitational stability.
So when processing a rare snail image, the contrastive loss function mathematically incentivizes the network to pull the snail's feature representation closer to the well-established prototype of the turtle.
Which resides in the data-rich head class.
That is so clever.
It really is. The tail class is borrowing gradient stability from its semantic neighbors.
Because it doesn't have enough data to build its own stability.
Right. It doesn't have to learn the complex geometries of what a protective shell looks like entirely from just 3 snail samples.
It can just leverage the optimized feature representations that the turtle class already figured out.
Exactly. This balances the feature space by structurally supporting the rare classes with relevant generalized knowledge.
But I do have a pretty major pushback here.
Okay, let's hear it.
The obvious risk in this dynamic is feature collapse.
Yes, feature collapse.
Right, because if the contrastive loss pulls the snail's representation too aggressively toward the turtle's prototype, doesn't the model risk eroding the actual interclass boundaries?
That is the danger, yes.
Yeah. It might achieve stability at the cost of its unique identity, resulting in a model that simply misclassifies all the snails as turtles.
Which defeats the whole purpose.
Exactly. How does it keep its unique identity?
Well, the researchers control for identity loss by strictly modulating the scalar temperatures within the contrastive loss function.
Okay, scalar temperatures, what are those?
They are specific hyperparameters denoted in the math as tau and tau prime,
Tau and tau prime. Okay.
and they control the sharpness of the softmax distribution.
The sharpness. Meaning what exactly?
By maintaining relatively low temperature values, so for instance setting tau to 0.1 and tau prime to 0.2, the loss function heavily penalizes slight deviations.
Oh, I see. A lower temperature sharpens the distribution, meaning the model maintains a very low tolerance for blurring the actual class boundaries.
Right, it's very strict.
So it allows the rare sample to align with the shared multigranularity features, like the texture of the shell,
Yes.
but without collapsing into the distinct primary prototype of the head class.
Exactly. It borrows the structural architecture without losing its unique classification.
That's brilliant. So the temperature effectively governs the transfer rate of the semantic knowledge.
It enables a guided, highly controlled knowledge transfer. It maintains the interclass variance while optimizing the interclass compactness.
Okay, the theoretical mechanics are incredibly elegant, but the validation requires examining the empirical performance.
Right, we have to see if it actually works in the real world.
Yes, on heavily skewed benchmark data sets. And the paper specifically looks at CFAR 100 LT, CFAR 10 LT, and ImageNet LT.
All standard benchmarks for long-tailed problems.
And evaluating these models requires segmenting the performance across many-shot, medium-shot, and few-shot distributions, right?
You have to, yes. Otherwise, the head classes will just mask the failure of the tail classes in the overall average.
Right, and the standard evaluation metric here is top 1 accuracy.
Meaning, did the model's very first guess match the actual image?
Okay, so when they benchmarked this SKCL framework against BCL, which is Balanced Contrastive Learning, a highly regarded baseline, the results on ImageNet LT were pretty definitive.
They were very impressive.
Yeah, on the few-shot classes, which are the rare ones, SKCL delivered an absolute improvement of 5.0%.
A 5% jump in top 1 accuracy on few shot classes is massive.
It really isolates the efficacy of that semantic pulling we just talked about.
Absolutely, because DCL fails here, since it primarily relies on just reweighting the loss based on class frequency.
Oh, so it treats all rare classes as equally isolated.
Exactly, whereas SKCL actually understands the contextual neighborhood.
But honestly, the most significant data point to me here is how SKCL handles the many-shot distribution.
Oh yeah, the many-shot results are the real breakthrough.
Because historically, boosting tail performance triggers this zero-sum trade-off where you end up degrading the accuracy on the head classes.
Right, the AI Robin Hood problem. You rob from the rich classes to give to the poor classes.
Yes, the Robin Hood problem that has plagued long-tailed classification for years, but SKCL bypassed this trade-off completely.
It really did.
While boosting the few-shot classes by 5%, it simultaneously improved the many-shot classes by 4.3% over the baseline.
Everyone wins.
Exactly. The rising tide lifts all boats.
Right.
And it's because the knowledge transfer isn't just an arbitrary statistical redistribution.
No, it fundamentally improves the model's generalized feature extraction.
By mapping the relationship between the snail and the turtle, the network's foundational understanding of the concept of a shell just becomes more robust across the board.
Right, which naturally improves its confidence on the data-rich head classes as well,
Yeah.
because it actually understands what it's looking at now.
That is so cool. And they also benchmarked SKCL against concut mix, right?
Yes, concut mix, which is a state-of-the-art data augmentation technique.
And data augmentation is basically trying to solve the data deficit via brute force,
Right, it mathematically blends image patches to synthesize artificial training samples.
which sounds computationally exhausting.
Oh, it is incredibly expensive computationally, and it scales very poorly.
But SKCL outperformed concut mix overall.
It did, which demonstrates that extracting latent semantic knowledge up front via an LLM is just a far more efficient mechanism.
Right. It's more effective for representation learning than continuously synthesizing artificial pixel data. It really validates the hypothesis that injecting prior semantic knowledge produces a more generalized, robust architecture than just relying purely on data augmentation.
Absolutely.
Well, we've traced the pipeline today from identifying the flaw in those rigid topological hierarchies like WordNet
Right.
to standardizing LLM outputs into a 384-dimensional vector space, mapping the semantic similarity matrix, and then finally executing that guided contrastive loss via the temperature-controlled prototypes.
It is a phenomenal framework. It effectively solves the zero-sum trade-off in long-tailed distributions.
It really does. And I think for our listeners, the big takeaway here is that this methodology signals a crucial shift in how we approach representation learning.
Yeah, we're finally moving away from the assumption that the only solution to a data deficit is synthesizing more data.
Exactly.
Yeah.
By grounding the vision architecture in macro-level semantic relationships, the model operates with a degree of contextual awareness that really mirrors human cognitive inference.
It's not just counting pixels anymore. It's understanding concepts.
Right, which introduces a really interesting trajectory for future multimodal development.
Oh yeah, where do you see this going?
Well, in this specific framework, the text-based LLM is acting as the teacher-eth. It's guiding the vision model's understanding of the physical world based entirely on linguistic correlation.
Where the text is teaching the eyes.
But as vision models achieve this level of robust multi-granularity physical grounding, the representation of spatial and physical reality will likely surpass the text-bound LLMs.
Oh, that's a fascinating point.
Right, so the logical progression is a complete reversal of this dynamic, where grounded vision models are eventually utilized to constrain and correct the physical hallucinations of language models.
I love that. When the vision models start telling the LLMs, hey, that's not actually how gravity works, or that's not how a physical object bends.
Exactly. The eyes will eventually correct the mouth.
And the architecture we explored today really establishes the necessary semantic bridges to make that kind of bidirectional grounding possible in the future.
It proves that contextual knowledge transfer is just far more powerful than isolated feature extraction.
Completely agree.
The bottleneck of long-tailed classification isn't just a lack of data, it is a lack of context. STCL provides a scalable blueprint for building models that actually understand the relationships between the features they extract. Thanks for joining us on this deep dive.